Hi everyone, my name is Tomek Masternak. I'm an engineer at Particular Software when I build distributed systems and platform for building distributed systems. In this presentation, I will be talking about checking safety in exactly once, which is a library that I built together with my friend Szymon Pobiega. Let me start with describing the problem and the challenge that distributed system builders face when they use messaging infrastructure. What is currently a de facto standard, both when it comes to the infrastructure which is available on-prem or in the cloud, is at least once message delivery guarantee. So that changed quite some time in the past. Before, we used to have a two-phase commit available and distributed transactions. That's pretty much no longer the case, and currently at least once message delivery is a reality that everyone has to work with. Now, at least once message delivery can be challenging from the system builder perspective, especially when writing logic for handling messages that arrive or are being pushed from the messaging infrastructure to the receivers. So let's go through a hypothetical situation just to see what kind of situations I'm talking about. So let's assume that there are some messages in flight, 1, 2, and 3, and that is the order in which they are stored in the messaging infrastructure or in the queue. Because of the way how the at least once message delivery works, is perfectly possible for a message to be redelivered or delivered multiple times to the receiver. And this is usually caused by this is usually a simple consequence of the fact that the messaging infrastructure will not consider a message to be delivered until it gets an acknowledgement from the receiver. So whenever that acknowledgement does not arrive or does not arrive in a given period of time, the message will reappear in the queue and will be processed or delivered once again. So from the processing perspective, what is possible is that some messages get duplicated. In our situation, it's message 2. What's also possible is reordering. And this usually happens when a messaging infrastructure has some delivery or processing timeout. So whenever a message is picked up by the receiver, the timeout starts, and if it reaches a threshold, that message will reappear in the queue one more time. And potentially, in the meantime, other messages might be successfully processed, so the effective ordering of processing at the receiver end will be different than the original ordering. Finally, both of those situations can happen independently at the same time. So the end situation is that it's perfectly fine for the messages to be reordered, and it's perfectly fine for messages to be duplicated. And now that can be a challenge from the system builder perspective. A very common and standard solution to that situation is idempotency, which basically means that whenever a duplicate of the message is received, the end result of processing that message should be the same as for the first processing of that message. And very often this is understood, or this boils down to the message processing logic being deterministic. This is this is often the case in remote procedure call type of systems, when there is only a single message in flight or a single call in flight, and that call will be repeated over and over again until a successful acknowledgement comes in from the remote invocation. Now, that might be not enough if there are more than one message in flight, and this is very often the case when we are building and modeling business processes. And this is a very simple example which shows what might be the problem. So what we are looking at here is a simple sequence diagram showing a behavior in a system which models or implements a shooting range game. So there is a handler, shooting range, which is responsible for holding a piece of state, which is the current target position of the target. And the players can attempt to fire at a given position, and the shooting range is responsible for sending back a response saying whether the attempt was successful or failed. So what we can see here is a situation in which we have a shooting range, and the shooting range is set to target position 42. And then we have a player that fires at position 42. And the response from that call is a hit. After that, the target is being moved to position 1. And finally, an interesting situation happens because we get a duplicate. A duplicated fire at message, which was already processed once, but it's being reprocessed one more time. And the logic is deterministic, but the response that we get is a miss. So what happened in that scenario is that we have a single logical message being delivered twice, and each of the processing of those this message results in a contradictory result, contradictory side effect, which is usually far from what we are expecting from the systems that we are building. And the obvious problem that we have here is that even though the logic was deterministic, the state changed significantly in between the first processing and the duplicate, which resulted in that behavior. So what it shows is that the deterministic logic is not enough. We also need to think about the state, and either we need to capture the side effects and basically redo them whenever a duplicate comes in, or we need to be able to get a handle at the historical state as it was when the message first arrived. So what we are assuming in the library is that the distributed system that we are talking about is built of a bunch of handlers. Each handler has a separate dedicated piece of state that handler is the sole owner. And the only possibility to communicate between the handlers is via sending messages. So what each handler is doing is that it picks up the message from the input queue, executes the business logic, which results in state update, and puts a message in the output queue. And the main idea or goal of the library was as stated here, to make sure that the observable side effects correspond to some serial execution of input messages with atomic commit guarantee between the business store and the output queue. So basically what we wanted to make sure is that whenever a duplicate comes in, the side effects that we will produce on the state and in terms of sending out the output messages is the same as if there was a single processing and the ordering is corresponding to some possible serial execution. The implementation of the library is based on the Azure stack, and it can run in Azure Function Host, which basically means that all the messaging infrastructure available for Azure Functions is available there as well. And the state is stored in Azure Cosmos DB. Specifically, what we rely on in terms of Azure Cosmos DB is that it provides optimistic concurrency control, which is pretty important, or the key part of the approach that we are taking. We store our infrastructural library driven data in a separate logical partition, which also comes with a consequence, which is that there is no atomic transactions between the business state and the infrastructural state. And we assume that the users are using Azure Cosmos DB with session consistency model. Finally, high performance scenarios are out of scope. It's not something that we focused on. Good enough performance, whatever that means, was our goal. Now, the general idea of the algorithm is as follows. Whenever a message comes in, we check whether we already processed it. If not, we load the state, we run the business logic, And we do not send out the output messages, but we capture them and store in the store. Now we attach a single correlation ID to the business piece of data, and then we commit it to the business logical partition. And this is where we do the optimistic concurrency check. So we do that only if that entity did not change since we loaded it from the store. And if that is successful, this is basically a commit in the or this is the point of no return in the atomic commit protocol. Once that is done, both parts, which is the business state, which is already committed, and the output messages will be committed eventually. Now, an important thing here to notice is that during some failure situations, what can happen is that the output messages might be sent out multiple times. However, because the duplicates can happen with at least once message delivery already, we can say that we are hiding behind that failure mode. So basically, because the duplicates can be already there, we can produce duplicates because whoever is processing them should be and is expected to cope with that situation. Okay, so that was the general idea about the problem and the solution that we seeked and wanted to implement. And now I wanted to talk about the TLA plus model and how we use that model to validate the safety. So the goals of the model was to make sure that our algorithm works not only in the happy path, but also when the things get bad. And as we all know, it's very easy to show that the algorithm sometimes works, but it's actually very tricky to figure out all the border case scenario. So we wanted to make sure that we have some validation, some model checking done to make sure that that we actually are convinced ourselves that the algorithm does what we wanted it to do. And specifically what we wanted to check was the safety properties. And those safety properties were described as atomic commit. So basically we wanted to make sure that when we commit to the business logic store, we eventually push out the changes to the output queue and also make changes to the input queue. And also we wanted to make sure that the side effects are consistent in a way that even for duplicates, there is only one change in the business state, and that the output messages and the business state change were made over the same version of the business state, which I think will be a bit clearer when we get to the formulas. And finally, we wanted to make sure that everything works as expected, even without atomic transaction between different logical partitions, because as I stated, we stored the business logic and the infrastructural data in a separate partitions. Obviously, there were most of the things that were in the implementation did not make it to the model, and specifically, we did not model the cleanup logic, which is responsible for clearing the infrastructural data that is stored by the library. We did not model the log leases that are used to lower the chance of concurrency collisions, optimistic concurrency check failures, basically. And we also did not model the exponential backups and processing retries, which are there to make the library a bit more performant in the failure scenarios. Okay, so let's look at the specification. This is the main part of the process that models a single handler. Most of the labels are folded, but that shows the main structure of the specification. So what we have here is an infinite while loop, and in that loop, the process is trying to pick up a message from the input queue, then it checks by looking at the transaction field on the state whether it needs to redo some of the transactional steps to basically push out the changes that are still there and not pushed to the output queue. And after doing that, we check whether we already processed that message. If we did not process that message, we model the business logic execution, capturing the side effects, storing them, the optimistic concurrency commit to the business store, and then pushing out the transaction to the until it's finished. And the main reason why we used class calc was that the syntax was more familiar for us, and secondly, that it actually corresponds pretty well when it comes to the implementation that was done in C#. So we were able to look at the code side by side, and the specification corresponded pretty well with what we could see on the screen looking at the real implementation. When it comes to state modeling, there wasn't that much happening. Two important notices is that the input queue was modeled as a set, but that set had records with two fields, one which was the logical message ID and duplicate message ID. So the way how we modeled the duplicates was basically by starting off with duplicates already in the input queue. When it comes to the business store modeling, we were storing a sequence which was a history of snapshots of the states as they were throughout the execution of the algorithm, and that was pretty useful when writing the invariants. And we also modeled the version for the optimistic concurrency check. All the other bits were used to model the infrastructural storage and the output queue, which was also a set. Another interesting bit is that we did not use a default termination formula. So what we said was that the processes were running in the infinite loops, but the proper termination of the algorithm was a situation in which all the processes were in the lock-in message and the input queue was empty. So basically, the termination was modeling a situation in which the input queue is drained and none of the handler is doing anything in specific, but waiting for anything to appear in that input queue. Finally, the safety invariants. So this is what we ended up when it comes to safety, and that basically models or expresses the safety property, which makes sure that for any logical message, there is at most once change happening to the business store and at most once message being produced and sent to the output queue. And those are the first two parts, one on the top and one in the middle. And finally, the one which is called consistent state and output says that if the message is fully processed, the version on which the version for the business state and the output message should be the same. So basically, we make sure that those two pieces of side effects are consistent in a way that they operated and were produced by a business logic operating on the same version of the business state. Another interesting bit is how we modeled failures. So what we ended up was a macro that basically was a single instruction, which was go to main loop, which basically meant that model the situation in which either the process restarts or some exception is being thrown, and we basically catch it at the top of the stack and go back looping in that infinite while loop. And the way that we used it was that whenever a failure was possible or we wanted to model a failure, we would do either or expression. So for instance, in the commit state macro, you can see that if the optimistic concurrency check results in true, we either commit right to the store or we fail. And that was a general approach to modeling those kinds of failures. Okay, so now a few words about the results. So there were expected and unexpected results. When it comes to expected results, those were obviously bugs that we found in various parts of the algorithm, specifically in the post-failure commits, and also in the logic that assigns the transaction ID. And as I said, that was something that we wanted to get from the model checking. So that's why I called it expected. I don't want to say that it's or deprecate the value of that, because that was exactly what we wanted. However, there were also unexpected bits, and I would say that the main unexpected bit was the fact that when we started off writing the model, we realized that we don't really understand what is it that we are actually doing. So it actually forced us to distill the algorithm to its essentials and to make sure what are the assumptions that we are making, which are pretty important, and also what are the most important steps in that algorithm. And as a follow-up of that, we realized that there are actually some extensions that we could also use. So for instance, I already said that one of the main assumptions that we are making is that we don't need any kind of a prepare phase for the output queue, because we can always commit to that output queue. We can always send a message there. And the duplicates can happen there because there's already that failure mode which we need to cope with. But what we realized is that there might be some other resources that are always able to commit. So for instance, if we have some kind of a write once store. So for instance, a blob store with a GUID blobs that can be written only once, that could be an extension to that algorithm as well. And that could be a supported side effect that we could apply the same way as we are sending out the messages. Finally, what we realized is that we did not know the Cosmos DB well enough and all the memory model implications. So we had to go back to the drawing board and understand what does it mean that we are running in a session memory model, and also that there are no atomic transactions between the logical partitions. And finally, another unexpected thing was that in order to create a meaningful model, we had to understand what are the concurrency characteristics of the algorithm. So what are the parts that can happen independently and concurrently. But even more importantly, we had to learn what are the failure modes, or what are the failure situations that can happen in different parts of the system as well. So it actually forced us to understand the technology that we were using far better than we knew it beforehand. So we did a validation, we did a model checking, and an interesting note here is that whenever there was a bug in a specification or in the algorithm, we were able to find it on a very small models. And by very small models, I mean a single message with a single duplicate and a single process, almost that. So in that sense, the running time of model checking was never a problem for us, because whenever there were bugs, we would get a feedback immediately. Now, that being said, after we settled on an algorithm and we checked it with a smaller model, we also went with a bigger one. And the bigger that we did was 2 processes with 6 messages in the input queue. Those are the numbers in terms of number of states that we ended up with. And that was running roughly 2.5 hours on a laptop, my personal laptop, that I would consider a high-end laptop based on current standards. Okay, that's it that I prepared for you in this presentation. If anyone wants to know more about the work that we did around TLA Plus and the library, we are posting about that at exactly once GitHub.io. I'm also available on Twitter at Masternak. So if anyone wants to chat, please reach out to me. I really like to share ideas. Thank you very much.